Hello, this is Miss Rich, and we are working on our video for describing relationships. This is section 3.1 and 3.2, mostly from 3.2. And I want to go over some things that we touched on in class and continue a couple things as well. Let's get started. We talked in class about this first regression, this scatter plot. A regression line is a line that describes how a response variable y changes as an explanatory variable, which is x, changes. And here we had this data came from non-exercise activity, which meant activity. They were trying to see if people who were particularly fidgety or wiggled a lot, perhaps, and see if that affected the amount of fat that they gained over an 8-week period. So 16 healthy young adults were in the study, and they were fed an unusual amount of food over this time. And as you can see, we ended up with a negative relationship here, and we put in the line of best fit, and it's clearly has a negative slope. And we would describe this scatter plot as the plot shows a moderately strong negative linear relationship association between NEA, non-exercise activity, and fat gain with no outliers. So notice when we describe a scatter plot, we need to put strengths. It's strong, moderately strong. We're looking at how spread the dots are from each other. What its direction is, meaning either negative or positive, and its form, which at this point is going to be linear or nonlinear. Later on, it could also be logarithmic, exponential, things like that. And so what this negative relationship actually means is, of course, as non-exercise activity increases, our fat gain is decreasing. And so that in context means, and know that that's in general. It is predicted. Not every value, if you go from this dot up here, for instance, from here to here, that's not necessarily changing the same way as it will be if you follow the line. So it's just in general what's happening as your non-exercise activity increases. Okay, we mentioned residuals. Residuals is our actual vertical deviation, vertical distance. The actual points, so these points are the actual points we got from our study, deviate from the predicted values, which would be the points that would fall on the line, from the prediction line, which is here, our regression line. A residual is calculated, the observed value, which is what we, again, get from our data, minus the predicted value. And the predicted value, that y hat value, is going to come by plugging into an x value. So, for instance, if you want to find this residual right here, the size of that residual, you would plug in that x value, which would be 136 or so, in for the x and get your y hat, your predicted y, and then you would subtract it from what the actual y was, which is what you would get out of your data to get your residual. Positive residuals are, of course, above the line, and negative residuals are below the line. Always that vertical distance from the prediction. One of the first principles of data analysis is to look at the overall pattern and for striking departures from that pattern. A regression line describes the overall pattern of a linear relationship between two variables. We see the departures from this pattern by looking at the residuals. And this is where a residual plot comes in. If you take the plot and basically turn it horizontally like so, that gives you a residual plot. Residual plot, is going to be the same x values here against the residuals, which we just discussed are y minus y hat, each y value minus the actual minus the predicted. And so when we look at these residuals, we're looking at a couple of different things to tell if it's a good model. First of all, the residual plot should show no obvious pattern. If you look at these two residual plots here, they have these obvious curves, and they will be very obvious curves. And if that happens, you want to say, well, there was, because of the curve in the residual plot, that there is probably a more appropriate model rather than a linear model. It doesn't necessarily talk about how strong the model is, the linear model is, but it does tell you that there's a more appropriate model. This is not the best model. Also, the other thing is your residual should be relatively small in size. Now, this is often a judgment call as to what is small in size, but what's meant by this, if you have a residual plot and you have points that start out pretty close to your residual line there, and maybe fan out as you go, kind of like this, you'd want to talk about what that means in respect to the data. Here, this data down here, below this x value, is obviously much closer to the line. So the line would be a better prediction below this given x value than it would above it. So if you have a fanning out on your residual plot, you want to talk about that. The size of the residuals are getting larger as x gets larger in this particular one. Now, do know that you will occasionally come across S in a computer printout generally, which are the standard deviation of the residuals, your little s. Standard deviation of residuals is very helpful because if you tried to find, well, approximately how far are the points from the line? Well, if you averaged all the residuals, then you would always get 0. You're averaging all these positive distances from the line with all these negative distances from the line. Of course, you would always get 0, so that wouldn't be any help. But the standard deviations of the residuals, which is essentially, so here's a residual, y minus y hat, square it to get rid of the negatives and positives, and essentially average them up, and then square root it again to get it back to out of the square, back to the same units as the residual. You can see that that S would show you about how far off each point is from the line, which can be very helpful. Know that S is different from the standard deviation of X or the standard deviation of Y, which would be S of X or S of Y. Now, there's a lot you're going to see when you see a computer printout. Here is a mini-tab version. First of all, S right here is what we were just talking about, the standard deviation of the residuals. And it's predicted right here. It's how I would find a good way to predict it. This S, the standard deviation of the residuals, tells us that on average, the prediction error of fat gained from the model is 0.739. That's how far off the points are from the line on average. This value, R squared, is your coefficient of determination, which is interpreted right here. R squared tells us that 60.6% of the variability in fat gain is accounted for by the model with non-exercise activity. That's kind of the little sentence we're going to use to talk about R squared, and we discussed this in class. We'll see it again on the next slide. It's discussing that improvement by adding that X value in the variability. We'll look at that in a minute. As well, you can get your whole regression line right here, fat gain hat equals 3.505, so that's our y-intercept. Our y-intercept is going to be found right here, which is under coefficient and next to constant, because it's the coefficient of the constant, which means it is the constant, minus 0.00344. That's our slope under coefficient and next to the x value, NEA. And make sure when you write out this regression equation, you put it in context like we've done here. To interpret the slope of B. Now remember, in regression, we call slope B and the y-intercept is generally a. The slope b equals negative 0.00344 tells us that the amount of fat gained is predicted to go down by that amount for each added calorie of NEA. So each 1 unit increase in X is how much is predicted to be changed for the Y. Make sure you include that predicted. That is key, because this isn't going to happen every time. That's just what the line is predicting that it'll happen on average. The y-intercept of 3.505 kilograms is the fat gained, so that's your y value, estimated by this model if NEA does not change. So y-intercept is going to be interpreted when X is 0, NEA is 0, then your y-intercept is 3.5. Your fat gain is 3.5. Now remember, this often won't be valid for the type of data you have, but here it does make sense, because if you're eating a lot of food and the NEA doesn't change, you still could be gaining weight, of course. Okay, other important equations for the least squared regression line is when you have to find the regression line and maybe you're not given slope and the y-intercept, maybe you're only given standard deviation of x and y, maybe you're only given r, which is correlation. This equation here is very commonly used. It's on your formula sheet. It's probably the formula that you will refer to most on your formula sheet that you'll actually use. And its slope equals the correlation r times the standard deviation of the y divided by the standard deviation of x. That's how you could find